Okay guys, in this video we are going to talk a little bit about quantum mechanics as a theory, and we'll review some of the key concepts that we need to understand before we can move on to the electronic structure of atoms. So we'll start with an idea proposed by Louis de Broglie in 1924. He postulated that microscopic matter, like photons, exhibits a particle-wave duality. So Einstein used his understanding of the photoelectric effect to explain that light exhibits particle-wave duality. Sometimes light behaves like a wave, for example, when light diffracts or exhibits interference effects. However, in the photoelectric effect, the photon exhibits particle-like characteristics. De Broglie extended the idea to include matter. That is, matter has both a particle and a wave duality to it. At least microscopic matter does. And de Broglie derived a relationship for the wavelength of a material particle. This lambda is given by Planck's constant divided by the momentum of the particle. And momentum is a quantity in physics that is equal to the mass of the particle times its speed. So the wavelength is Planck's constant divided by the mass times the velocity. The idea here is that because electrons within atoms have a wave-like characteristic, and those waves are confined within the atom, then those electrons will exhibit standing waves. And recall from our previous discussion that standing waves exhibit restricted wavelengths and hence quantized energies. So what de Broglie's idea does, what his postulate states, is that because electrons have a wave-like character to them, whenever you confine an electron within an atom, you end up restricting the wavelengths associated with that quantum mechanical particle, which leads to quantized energy levels. This effect has been demonstrated experimentally. So recall from our previous discussion that if you shine light on a screen that has two slits in it, you will observe a diffraction pattern for the light. Right? This has to do with the wave-like characteristics of electromagnetic radiation. It turns out that this effect can also be shown for electrons. That is, if you shoot electrons at a screen that has two slits in it, what you will observe over time is the buildup of an interference pattern, which is attributed to the wave-like character of electrons. Okay, so de Broglie's postulate is experimentally grounded in the sense that electrons exhibit diffraction just like classical waves do. So here in this problem, we are doing just a few calculations to get a sense of what the wavelength is for various particles. So in part A, we are actually going to calculate the wavelength for a macroscopic particle that has a mass of 1 kilogram and is moving at a reasonable speed of 1 kilometer per hour. So we want to use the de Broglie formula, Planck's constant divided by the mass of the particle times its speed. And we're going to want to convert everything to SI units here. So we'll put in the Planck's constant, 6.626 times 10 to the minus 34 joules seconds. The mass is 1 kilogram, so we're going to leave that in SI units. And then we need to do a little bit of work here on the speed. Okay, so we've got 1.00 kilometers per hour. And we want to convert those kilometers to meters, so we're going to say there are 10 to the 3 meters per kilometer. and we want to convert the hours to seconds. So in 1 hour, there are 3,600 seconds. Okay, so that'll get everything in SI units. So running these numbers through our calculator, we're getting something like 2.38 times 10 to the minus 33 meters. Okay, now that is an extremely small distance. In fact, if you think about the size of things, the nucleus of an atom is on the order of 10 to the minus 15 meters, which is more than 15 orders of magnitude larger than that wavelength. So because this number is so small, there's absolutely no way to observe a wavelength that's that small. You cannot create a hole, a slit in a screen of that dimension, okay, because it's smaller than the nucleus of an atom. So effectively, the wave-like character of macroscopic objects cannot be observed. Let's do the calculation now for an electron. Okay. Let's do the calculation for an electron. It has a much smaller mass, and then it can move at all sorts of speeds. So here we've got an electron that's moving pretty fast, over 1 million meters per second. Let's calculate the de Broglie wavelength for that electron. So we've got our Planck's constant, and we've got our mass, 9.11 times 10 to the minus 31. This is the big difference here. Microscopic particles have incredibly small masses. So there's the mass, and then now we need the speed, 4.19 times 10 to the 6 meters per second. That makes a difference as well because it's moving so fast. And you get something that's 1.74 times 10 to the minus 10. Okay, and so that's 1.74 angstroms. Also very small. However, it's much, much larger than the wavelength for a macroscopic particle. This distance is comparable to the distance between atoms within a crystal. And so in principle, it's possible to shine electrons through an opening that's that small and then observe the diffraction pattern. Okay, so the wave-like characteristic of electrons can be observed. However, the wave-like character of macroscopic particles cannot be observed. I'm going to go ahead and let you do the part C calculation yourself as a practice problem, and then I'm going to move on to, these problems here are the same. Here you're doing the same calculation for a softball that has a mass of 100 grams moving at 35 meters per second. Again, you're going to find that that softball has a very small de Broglie wavelength. However, the proton here is going to have a larger wavelength. We're going to go ahead and move on to the last couple of concepts here. Another idea in quantum mechanics that's significant is the idea of uncertainty. So because matter has a wave-like character, the particle the particle should be described by some type of wave mathematically, and that type of description is called a wave function. And in the mid-20s, Schrödinger, German theoretical physicist, he predicted, or he derived, or arrived at rather, an equation that describes the electron wave. So think of, you can kind of think of psi, this is the Greek letter psi x of t, as it's a mathematical representation of the electron's wave. Okay, so you can think of it, it's some type of function that oscillates as a function of x, right? The amplitude goes up and down, and then that wave moves in time. Okay, so the wave function describing the electron is a function of position and time. It turns out, based upon the mathematics of Schrodinger's wave function, that the precision with which you can measure certain quantities about the particle is fundamentally, intrinsically limited. So for example, what we're looking at here, this delta x, this represents the uncertainty in measuring the position of an electron. And delta p represents the uncertainty in measuring the momentum of the electron. You can also write that in terms of the uncertainty in the velocity, measuring the velocity of the electron. It turns out the mathematics of quantum mechanics requires that the product of these two uncertainties have a finite value given by h bar over 2, where h bar is Planck's constant divided by 2 pi. And what this tells us, the important point, is that one cannot simultaneously measure the position and momentum of an electron with complete certainty. Okay, so you can't improve the experiments for measuring these quantities indefinitely. There's going to be some fundamental limit to your ability to know where the particle is and how fast it's moving at the same time. And this is a rather striking contradiction from classical physics. In terms of classical thinking, you could always design, at least in principle, you could design a better experiment that would give you better precision in your measured quantities. Quantum mechanics and the mathematics of quantum mechanics tells you that you cannot do that. There is some fundamental limit to what you can know about a microscopic particle. This implies that there is some inherent randomness in the nature of microscopic particles like electrons and protons and atoms. This is very different from classical physics. In classical physics, particles, they follow well-defined, localized trajectories. That is, you can map out the position of a classical particle as a function of t, and that trajectory is described explicitly by Newton's equations of motion. For microscopic particles, we do not have a trajectory per se. What we have is a wave function, which is a non-local object, right? The wave extends outward in space, and it moves around in space. And according to the Heisenberg uncertainty principle, it has an inherent uncertainty associated with it in the sense that you cannot predict the outcome of an individual experiment. You can really only predict the statistics of an experiment that's repeated many, many times. This is known as the Born interpretation of the wave function. Born interprets the wave function as he interprets the square of the wave function as the probability for predicting the outcome of a measurement. So for example, if you were to do a measurement of a particle's position, in order to assess whether or not a particle is at a given value of x, you don't know it for certain. However, you can predict the probability that you might find the particle at that particular position x at a given time t. Okay, so there's this inherent statistics to quantum mechanical theory that essentially limits your ability to decisively say where a given particle is. You're limited to discussing only the statistics or the probability of finding the particle at a particular point in space. And that's because microscopic particles are inherently non-local objects. So that's the idea here with this Born interpretation of the wave function. Well, we are just about ready to start discussing the electronic structure of atoms, and so I'm going to save that for the next video, and I'm going to stop this one right here.